This is another titration of a base, this time methylamine. So we identify the salt that's going to be produced as the methylammonium ion, so CH3NH3 plus and Cl minus. So Cl minus again will not react with water. It's the CH3NH3 plus that will do that. So in water, this conjugate acid of a weak base will regenerate the weak base methylamine, CH3NH2. And a side product of that will be the H3O plus. So our IREC table will help us to solve for the equilibrium amount of H3O plus. We'll start by solving for the number of moles of base that we start with in our neutralization. We're given a volume of 50 mils and a molarity of 0.1 molar. So that gives us 0.005 moles, starting moles of our base. And this, of course, would be equivalent to the number of moles of salt that we generate. So this would be equal to the moles of CH3NH3 plus. So this number of moles can go into our initial line on our IREC table. Under the methylammonium ion, we'll start out by saying we have 0 moles of product, and we'll immediately create X moles of each product. That'll cost us X moles of reactant. So at equilibrium we'll have 0.005 minus X moles of the methylammonium ion and X moles of each product. And if we want to convert that to a concentration, we would divide by the total volume. Remember that total volume is necessary to calculate somewhere along the line here. It doesn't cancel out the way it does in a buffer calculation. We can start by doing that. So the total volume would be equal to the sum of the volumes of base that we start with and the volume of HCl that we add from the burette to get to the equivalence point. We know the starting volume of base. That's our 50 milliliters, 0.05 liters. We must calculate the volume of HCl required to get to the equivalence point. That would be equal to the number of moles of HCl required to get to the equivalence point, 0.005 moles. We divide by the molarity of HCl, which would be 0.2, giving us a total volume of 0.025 liters, or 25 milliliters. So that total volume now, the sum of those two volumes, 50 milliliters and 25 milliliters, for a total of 75 milliliters, or 0.075 liters. So with that total volume in hand, we can now go back and develop our equilibrium expression to solve for X and the molarity of H3O plus. We'll do that using a Ka expression for the ammonium ion. Remember, it's a Ka because the ammonium ion is an acid, as evidenced by the H3O plus in the product. This will be equal to the molarity of the products divided by the molarity of the reactant, the methylammonium ion. Because in this type of problem, the two products have equal molarities, we can write the numerator as H3O plus squared. We can divide that by the methylammonium ion molarity. And now we're trying to solve for the H3O plus molarity. That only works if those two quantities are equal. We want to solve for the H3O plus molarity by isolating it on the left side of the equation. So we have that the H3O plus molarity is equal to Ka of the methylammonium ion times the molarity of the methylammonium ion. And we take the root of all of that. Ka of that methylammonium ion will be difficult to find, but we will be able to find the Kb of the conjugate base. So we can write the Ka in terms of that. We can write the Ka as 10 to the minus 14 divided by the Kb of methylammonia. The molarity at equilibrium of the methylammonium ion is the equilibrium moles divided by that total volume. We're going to try to get rid of that x. We're going to assume that 0.005 minus x is approximately equal to 0.005. So we have 10 to the minus 14 divided by, there's that value of the Kb now of interest, and then multiplied by 0.005 moles divided by 0.075 liters, the square root of that. That works if x is so much smaller than 0.005 that 0.005 minus x is approximately equal to 0.005. So we move along there, solving that, which is giving us the molarity of the H3O plus. We get a value of moles per liter, and we solve the pH for that by taking minus the log of that value.